All right. Chapter 7, my friends, are called networks. Children, chill. Okay, so chapter 7 is all on networks. So the first thing we need to do is talk about what a network is. Your vertices are now going to be called terminals. And your edges are now going to be called links. Okay, so nothing's really changed right now. We still have dots. They're just called terminals now. We still have lines that connect the dots. They're just called links now. So your theme for this entire chapter is finding optimal networks that connect a set of points. Okay, so somehow we have to connect all of the terminals or your vertices without making a circuit or path. Okay. So we don't necessarily need a path. A path can still be a network. We absolutely 100% do not want circuits anymore. Okay, nothing gets closed off. Okay, our job then is to make the total cost as cheap as possible. Anybody still need this up? All right, so here's an example of a network problem. And I actually like to go back to, since y'all are up on cell phones and all that happy stuff. So basically what we're talking about in this chapter is a way to reach cable out to your house. Okay, so it doesn't necessarily have to follow anything fantastic. It just has to reach you. It doesn't have to connect to your neighbor. It just has to get to you. So that's what we're trying to do here. We're going to do that by creating different types of networks. So your first network that we're going to talk about is called a subgraph. A subgraph is when I have edges. Why is my board off already? Edges that come from the original graph. Okay, so in other words, we can't use anything that's not already there. We can create networks that are called span, which means I have to use all vertices from the original graph. And we want minimal. So we're talking the total weight. Total. Sorry. Welcome to my board. The total weight of the network must be as small as possible. It's just that freaking corner. Total. It's just that corner. Let me try to rewrite it.
They don't even look like total.
There we go. Okay. All right, so we're going to practice using an original picture, creating these types of things. So, first thing, this is my original picture. They want me to be able to create a subgraph that uses 4 vertices from my original picture and 6 edges from my original picture. So I've put 4 dots down. What 4 dots from this original picture do you want to use? B. What else do you want to use? C, E, and F. Okay, the biggest thing when you create subgraphs and spans is you have to use what is already there. You're just not using all of it. It's just a subgraph is a piece of the original. Okay, so I've used 4 dots from the original. I now need to use 6 edges that were from the original to connect these dots. What edge do you want to use first? B to C. Okay, B to C was there. B to E. E to F. F to C. C to E. And B to F.
I thought you said they couldn't include.
Huh?
I thought you said they couldn't. Yeah.
We're not actually doing full out networks yet.
Oh.
You're okay. We haven't actually turned the subgraph into a network yet. Okay. Example number 2 on the right. A span. Anytime you see the word span, you automatically have to use every dot in this picture. Okay? You have to use every dot in this picture. So this is A, B, C, D, E, and F. So a span says use all 6 dots, and then they want me to connect these 6 dots using 5 edges from my original picture. What 5 edges would you like to use? A to B.
B to C.
B to C.
C to F.
C to F.
E to F.
E to F.
And E to D.
And E to D. If you wanted to, instead of using C to F, I could have used B to F. That's still a span with 5 edges. Instead of using that, I could have used B to E. That's still a span with 5 edges. Okay, so a span has to use all the dots, the amount of edges they tell you, and all of your dots have to be connected. Okay, example 3, we're back to a subgraph. Okay, we're back to a subgraph on the left. So a subgraph does not have to use all the vertices. They want us to pick 5 vertices to use. What 5 vertices would you like to use?
A, B, C, D, E.
A, B, C, D, E. So we're just going to leave off F. A, B, C, D, oh my gosh, and E. So I could have picked any 5 vertices from my original graph. Now I need to use 4 of the edges from that original graph to connect all of these points.
A to B.
A to B, there's 1.
B to C.
B to C, there's 2.
B to E.
B to E, there's 3.
D to E.
There's 4. That is awful. I'm so sorry. I'm not recalibrating the board right now. Those lines are actually supposed to connect the dots.
They do.
Okay, this middle example says a span. A span says I have to use all of my dots. So I need A, B, C, D, E, and F.
That's it, right?
Okay, I need to connect with 6 edges. Josh, give me an edge. You said what? A to B. Cozy, give me an edge. Nawan, give me an edge. Ivan, give me an edge. Any edge from this original graph. You said what? B to E. Okay? So that's 1, 2, 3. We've done 4. Let's see. Cat rice. Give me an edge. Give me an edge from the original that you'd like to add to this picture.
You don't hurry up.
Man,
AD.
Nice.
You can't use AD.
You can't use AD. There's no line there.
Oh, it ain't.
D and E. Okay. I need 6 total edges, so we need 1 more. What did you say, Melon?
Yeah.
You said E to F. Perfect. So there's a span that has 6 edges. The last one. I need a subgraph that has 6 vertices. So if I need 6 vertices, I'm going to need them all. A, B, C, D, E, and F. They want me to connect these with 5 edges.
A to B.
A to B,
B to C.
B to C,
B to E.
B to E,
B to F.
E to F,
B to E.
D to E.
What is work too?
No, because A is not touched. Every a subgraph and a span has to all be connected. You can't have an isolated vertex. So if you can just erase one of those lines to reach out to A, you're good. So now that's good. That's perfect. Questions?
So subgraph, it has to all be connected, right?
Yes. Subgraph and spans have to all be connected.
No matter if it's a closed circuit.
Yes. Okay, notice a span is 6 dots as well. So example 2 right above this one and example 3 right below this one, these two are exactly the same. You could have made them exactly the same. They have all 6 dots and they have 5 edges. So both of those answers would have worked for both of those problems. Okay. All right. Now we're going to get into no more circuits. Say goodbye-bye to your circuits now. Okay. So we are now going to talk about what they call trees. Okay. So a tree, formal definition is a network. Which means we're connected with no circuits of any length. Okay, so I still can't have any isolated vertices. I can't have it broken into components. It has to be all one piece. But now I need to make sure that there are no circuits in my graph. Sometimes circuits can be hidden, so you have to be careful. Okay, so take a look at letter A. If you had to choose tree or not, would you say graph A is a tree or not?
No, it's a tree. It's not.
I heard no and I heard yes.
It's not a connected graph.
It's not a connected graph. Oh, it's not a tree. This is not. You've got component 1 and component 2 that are not connected. In order for it to be a tree, there would have to be something that would connect those 2 pieces. So I would have had to draw So as soon as you see more than one piece, not a tree. Take a look at B. Tree or no?
Tree.
Tree. Take a look at C.
Tree. No.
No.
Tree. It's a close.
It's not.
Continue with what you were saying.
It's closed.
There is a circuit here. Oh. There is a circuit right here.
So it's not a tree?
So this is not. Yes, it looks like the pretty trees outside, like what you used to draw when you were a child. Here's my tree. It's a triangle and a stump. That does not mean that it's a tree in math class.
Why is it tree?
Okay, it's not a tree. There is a circuit. Okay, you cannot have any type of circuit. Take a look at D. Tree. Take a look at E. Tree.
No.
Take a look at F.
No.
No. There's actually several circuits here. Oh my gosh.
Still bored.
I'm over it. Okay. F is not. There are 1, 2, 3, 4, 5, 6 circuits in there somewhere. Okay. There are multiple circuits in that graph. What about G?
No.
It's a tree. It's a tree.
This one is actually a tree.
How?
It's
Where's it close?
It's not close.
It's not.
This is not a circuit. There's no dots in those corners.
Oh.
Let me see. Wait, explain it again.
There's no dots here.
Oh.
So that's not a circuit. Your circuits have to go from dot to dot. So if I start here and I follow, that doesn't close off. This is not a circuit. So this is a tree.
Wow.
So that'd be H.
Oh.
Tree too?
What about H?
Oh, no, H not. Because it closed the circuit from, the one with there.
This hot mess of life is a circuit.
Where?
It doesn't look like it, but this hot mess right here is a circuit.
If you take the
It closes off. I can trace that whole thing and close off without lifting my pencil. There is a circuit here. That's what I mean by sometimes the circuits are hidden. Okay.
You can't trace that whole thing.
Yeah.
The whole thing doesn't have to be a circuit. There can be no circuits anywhere.
Oh, I see what you're saying. Cause
It can't even be a tiny circuit. So like when I do this one, there's a circuit in this one, but it doesn't touch every dot. I'm not talking Hamilton circuit where I have to touch every dot. I'm just talking circuit. There can be no closed off portions of your graph at all. So be careful with that. I know you're all on the Hamilton track right now because of the last chapter. A circuit in itself, does not mean we have to touch every dot. A circuit just means, can I trace from one dot and get back to that dot without lifting my pencil? Does not matter if I trace every line. It does not matter if I touch every dot. So this is not a tree. There is a circuit there. So that's what's going to catch you. However, as always, I have a way to fix it for you.
Shortcuts.
Shortcut! Yay, Miss Smith! I mean, yay, these smart math people that gave Miss Smith this knowledge. That's what we're going to do. All right. So, observation questions for the graphs that are trees. Look at all the graphs that you put tree for. Is there some type of relationship between the total number of edges and the vertices that you have in each one of those graphs? So let's go back and look. Okay, if we look at B, we said that was a tree. How many vertices?
11.
There's 11. How many edges are in this graph? 10. D is a tree. How many vertices? 6. How many edges? E is a tree. How many vertices? How many edges? G is a tree. Vertices.
8,
Edges.
7.
What relationship do I have going on here?
They're all one less.
So in order for a network to be a tree, however many vertices you have, you should always have one less edge every time. So kind of like Hamilton circuits where you had the vertices and then each degree was one less. In a network, in a tree, your vertices and edges have that relationship. So your relationship, your edges equal your vertices minus 1. Or your vertices equal your edges plus 1. Is there a special term you can use to describe the edges in each one of those graphs? No, that's not what I'm looking for here.
Surplus. No.
What?
I just
Wing?
thought of a word that came in.
He's hungry.
He's like, barbecue wings. We talked about a special term,
A pet.
and I believe it was chapter 5 is when we started talking about it. We did talk about it a little bit in chapter 6.
A bridge.
These are all bridges. Every edge in a tree is a bridge.
Ugh.
Okay, these are all bridges. If I erase any one of these lines in any one of these graphs, it disconnects my graph. Okay, so they're all bridges. Oh, we're almost done. We've got one more drawing example, and then we're going to talk about always, sometimes, and never.
We have a whole page. That is not. Oh.
Oh, you have to write is always, sometimes, or never. Shh. All right. So,
We just want to break.
we're almost done. I will have you done by 11 o'clock.
Okay.
All right.
If you stop whining. Okay. Spanning tree. Spanning tree. So, this is a subgraph. That connects all vertices with no surface. Okay, so when they ask you to draw a spanning tree, my suggestion to you is first figure out how many vertices do I need to draw a spanning tree. A spanning tree says I have to use all vertices. So how many vertices do I need to use? 5. Vertices should be 5. If I have 5 vertices, for this to be a tree, I need how many edges?
4.
4 edges. So, draw me all 5 dots. We're going to do a couple examples, so if you can kind of draw
I
small.
ain't got no room for this.
No
You
room?
even got no room.
I gave you no room?
No,
I
literally.
suck.
We'll just watch.
Right, we'll just watch.
We'll just watch.
Relax.
There's no room at all.
No. Barely.
Can you stick it up like in the observation questions for graphs that are true? Listen.
We just watch.
Shut up.
We'll just watch.
When you don't have it in your notes, slow it back on. I don't want to hear you whine. Why?
I won't.
Okay.
Right.
Oh my. Woo! All right. So I have all 5 dots. I need to connect these dots using 4 edges from the original graph.
A to C.
A to C,
A to B,
A to B,
C to D.
C to D,
D.
D to E. Bam. There's a spanning tree.
Whew.
It's a really ugly looking spanning tree. Yeah, I'm gonna draw you another ugly looking one too, right? Ready? A, B, C, D, E. Give me another way to do this.
Can you do
You can go
B to C?
E to C.
Yeah, D to C.
You said D to C. Hold on.
I
Okay.
said B to
I'm getting too many though.
C to
Like,
D.
C to E.
okay.
Cause I got
Stop.
one that I want to check.
All right. Go ahead now, Ron. What you got? C to D.
No, I didn't say that. I
I
said
thought-
B to E.
Boy, I swear you said C to D.
No, he said that.
I'm hearing things. He didn't even say that. So I'm definitely hearing things. All right. D to E.
Can you do E to C?
E to C. Yes.
All right, this is what I got. All right, so can you do C to B and D to A?
Fantastic.
He
That's a
literally.
spanning tree.
Oh shit. No.
As long as you use lines from your original graph and you only use 4 of them, it's a spanning tree. So let me show you some other examples that I did. Or shall I say that Matt did?
What page you on with it?
These are all examples of a spanning tree that connect all 5 of those dots. Any of these would have been correct.
And you can't close them.
You just cannot create a circuit, which is why you only use 4 edges, because you'll never create a circuit that way. As long as you reach out to every dot, you'll never create a circuit that way.
The question is, how hard does this get?
Right.
Oh, just wait for your project for this chapter.
How to project.
It is on like Donkey Kong.
Is that project that we taking a nap?
This is.
We need to talk about the chapter 6 project.
This one's
Okay. Okay. So there are a couple properties that tell you that you have a tree. 1, there can only be one and only one path that join 2 dots. AKA there's only one edge that goes from dot to dot. There's no multiple edges here, ever. Okay. Property 2, every edge is a bridge. Okay. And property 3, if I have n vertices, I have n minus 1 edges. Okay. There's going to be a section on your test that's going to look like this. You need to be able to read these and tell me always a tree, sometimes a tree, or never a tree. If you answer sometimes, you need to draw me a picture that says it's a tree, and you need to draw me a picture that shows me that it's not a tree. Okay, so think about what a tree means and read these. So take a look at number 1. It says G has 4 vertices and 3 edges.
Always.
sometimes.
Why would you go with sometimes instead of always?
Oh, you weren't saying, okay.
So you rolled with they were
It
wrong.
could be sometimes because you can make it triangle with 3 edges, right?
Yes. Okay.
So I was
So
right.
this one is going to be sometimes.
That was right.
Okay. So a tree could have 4 vertices and 3 edges. That would be a tree. But I could also draw you one that looks like this. And that's not a tree. Because I have a circuit and it's disconnected. Take a look at number 2. They changed it up by adding one specific word.
Connected.
They've said now G is connected
Never. So,
with 4 vertices and 3 edges.
never.
Oh, wait.
This one is an always. Your key word here is connected. So connected means my picture has to look like this one on the left. Because my picture number 2 is disconnected. Okay, so you've got to watch for those keywords. That's what makes number 1 sometimes, and what makes number 2 and always. Okay, is that word connected? Or if you see the word bridges, if that said like 4 vertices and 3 bridges, that would be an always. Okay, so I need you to get specific to use always. Okay, take a look at number 3. 5 vertices, 5 edges.
Sometimes.
Never.
No.
Oh, wait, never.
Never. Why?
Because it has the same number.
This should have 4 edges.
Oh.
Or that should have 6 vertices. Okay, so please be careful with that. Number 4.
Always.
5 vertices, 4 bridges. That keyword bridges is what makes this one an always. Okay, so you're looking again for that word connected or that word bridges. Okay, number 5. This one's going to be a sometimes again because there's no connected or no vertices. I'm not drawing a picture. There's not enough space for 10. Okay. But if you would answer sometimes on a test for this, you'd have to give me a picture of a tree versus not a tree. Okay. What about 6, 10 vertices and 11 edges?
Never.
Never. Your edges are supposed to be less, not more. 12 vertices and 11 bridges.
Always.
Perfect. Connected with 8 vertices, and every vertex has a degree of 7.
Never. And you only have one line.
Awesome.
This one is going to be a never. Think about what degree of 7 means.
That means 7 lines.
That means 7 lines coming out of a dot. Every dot has to have 7 lines coming out of it. Remember, we said,
They're only bridges.
okay, they had to be bridges. So this one is going to be a never. Okay. Questions?
Nope.
10:57. Look at that. Okay, you do have homework.
We do have project.
There's only 5 problems to your homework tonight.
What am I saying?
Right.
Numbers 1,
Where's
2, 3 through 7 odd book pages on Canvas. Make sure you're going to chapter 7's book pages and not doing any other chapters book pages.
So basically 1, 2, 3, 5.
3, 5, and 7, yes. 1, 2, 3, 5, and 7. Okay, before you do that though,